Okay, welcome here to this video for Material Science 410, touching on some fundamentals for concrete testing for our second laboratory of the course. This lab will be completed by watching the lecture videos, this one as part of a series. In addition, there'll be some additional self-guided work that will be done individually. Here where you'll watch 3 additional videos here on the science of concrete, some innovations as far as making concrete building materials with smart materials and even shape memory alloys. And then you'll follow up by doing a Labster virtual lab experiment to simulate some lab work that one might do as they investigate the properties of cement before cure. Okay, so modern concrete is known to have various properties that you may be familiar with, and so we'll touch on those here. It's known that it's very strong in compression, but unfortunately pure concrete is poor in tension, and strategies to sort of address that involve reinforcement. Of course, you know concrete to be non-transparent. It's also insulating, and therefore plays a role in management of temperatures in building structures. It's also very hard, enduring, and lasts a long time, therefore, and is very corrosion resistant to contribute to that longevity. In the photographs here, you see some mechanical test fixtures addressing both compression and tension, touching on the mechanical properties in the first 2 bullet points. So concrete, as we mentioned, is high in compressive strength and is known to be made up primarily of fine aggregates in the form of sand. It may include ballast, a coarser aggregate, and cement, which is the binder, and water, which is an additive. And a fully cured cement begets calcium silicate hydrates, and these sort of calcium and silicon-based oxides end up in various ratios programmed by the formulation and can fine-tune the mechanical properties of the resulting cured cement. As we mentioned before, strategies to address the poor tensile strength can take advantage of including additives such as steel that will help balance the poor tensile properties and render the composite stronger in tensile loading conditions. As you might be familiar with, concrete has been around since the Roman era, and it is regarded as the most significant material involved in the development of that empire, dated back to before Christ here at 27 BC. So, as we consider how one assesses the quality of concrete at the kind of setting or cure stage, we have various techniques, and one that will be focused on in Lab 2 is the slump test. The slump test involves shaping a known amount and sort of specimen of concrete in its sort of flowing condition in a cone, and after removing the cone, allowing the material to sort of settle or slump and measuring the displacement relative to the height of that shaping cone. So a very simple test that has been used widely since 1922, and this is used to determine just how workable or how consistent the concrete is as we prepare to work with it. So you can imagine this is a good way to carry out quality control on various concrete batches as we prepare to kind of construct various structures with it. And the details of the slump test are outlined in something called an ASTM file for us here, and that ASTM C143, published in the US, is the resource for conducting a proper slump test. The slump value, as you can see, will be measured in a displacement here in inches, and it's can be somewhat programmed by not only the water to sort of cement ratio, but additional Fine-tuning occurs based on the properties of the materials, the mixing methods, the dosage, other admixtures, etc. So the slump test can sort of universally assess the quality of the workability of a cement, encompassing all those different sort of factors that can affect it. To elaborate on that, we know that things like the chemistry, or how much kind of reaction or hydration chemistry has occurred, the fineness of any included powders or particles, and the distribution of the size of those, and even the moisture content of the additives play a key role in affecting the slump value. The sort of history, meaning the temperature of the cementitious materials, the size, the texture, combined grading, cleanliness, moisture content of all those aggregates also plays a big role. The chemical admixtures, dosage, type, combination, interactions, if there's other chemistry happening there, sequence of addition, and all affect can arise with different slump values. Furthermore, the air content of a concrete, again owing to the sort of mixing type or conditions, can also affect the slump value, and even the transport methods and the equipment used can affect this, and of course the temperature of the setting concrete or the temperature of the mixing can affect this value, and ultimately, even the amount of free water that's present in the concrete affects this as well. Okay, so as you can see, the slump test can be used to sort of study lots of different factor levels for the factors listed here. And again, that displacement from the sort of shape of the cone versus the sort of offset from that shape of the cone is how we assess slump. So again, the slump value is typically listed in units of inches. So this 4-inch slump target is known to be a kind of a typical target to ensure that one can work with the material under a pumping condition, which is one of the more universally applied methods of applying concrete. Portland cement, as a specific form of concrete, it has no relation to the location Portland, Oregon, but instead is manufactured by crushing, milling, and portioning out a lot of starting materials. Those starting materials include calcium oxide or lime. This can be accessed from limestone, chalk shells, or calcareous rock. Another starting material is, of course, silica, formula SiO2, and this can be acquired from sand, reusing old glass bottles, even clays can be used, or even some forms of rock. Alumina is another starting material, formula Al2O3, and we can form bauxites or even use recycled aluminum or even some clays for this source material, as well as iron oxide can be included, so Fe2O3 formula there, and this can be accessed from clays, iron ores, scrap iron, and even fly ash. And lastly, it's known that gypsum can be applied, calcium sulfate as a dihydrate, and this can be, in fact, sort of found within limestone often to provide the sort of additive that way. Portland cement, when sort of on its way to being set, is known to therefore kind of take these starting materials and generate tricalcium silicate, dicalcium silicate, and even tricalcium aluminate, and the version there that includes the iron material there. So that is the tetracalcium aluminoferrite that can include that final iron oxide component. Okay, so the sort of binding quality of this Portland cement that is produced will be affected by the hydration reaction between cement and water and those silicates. So Portland cement ends up as a mixture of many compounds, as you can see, and 4 of these will make up about 90% of the weight of Portland cement. Okay, so those 4, as we mentioned, are listed as the tricalcium, dicalcium, and silicates, as well as tricalcium aluminate and that aluminoferrate. And you can see here a typical formulation for the Portland cement involves about 50 weight percent of the first one, 25 weight percent of the dicalcium silicate instead, and then 10% of that aluminate and that aluminoferrate at an equal kind of weight percentage of 10% there, and a little bit of makeup of the gypsum is a typical formulation here. The formula of these is listed at right, and so here you can see that the stoichiometry is changed between the first 2. We have sort of 3 units of calcium oxide to the 1 silica in the form of SiO2, and in the second case we've got 2 units of that instead. And in the last, in the aluminate, we've got 3-to-1 ratio there of that calcium oxide to that alumina. And in the final aluminoferrate, we have a balance between alumina and the Fe2O3 against 4 units of the calcium oxide. And again, the formula of gypsum is listed below. And again, there should be a 2 there. Apologies for the error there. Okay, so that is the main kind of introduction and background to the composition of concrete and the components listed therein. The next video will touch on the curing of these materials and how the hydration reaction leads to the mechanical properties that we witness in cured concrete.